I'm Jannik. Welcome to my talk on robust and verifiable proportionality axioms. This is joint work with Markus, and thank you very much for tuning into this video. Now, most of you are probably familiar with parliamentary elections or with proportional representation. And in most countries, it works quite simple. You have a few parties, and voters vote for these parties. And the parties have some percentage of the population that votes for them. For instance, here, the Labour Party has 14.1%. And then the seats in the parliament are apportioned approximately according to these percentages. So if you get 14% of the vote share, you should get approximately 14% of the parliament. But not all countries do this. In fact, the country I show you here, or in which this election took place, the UK doesn't do it. Instead, they use so-called plurality voting or first past the post voting, in which you have single districts in which a single candidate gets elected. Naturally, this is not proportional, since, well, if you are a very small party, let's say you have 10% of the population that votes for you, you will, in most cases, not win a single seat. So you would have 0 instead of 10 seats, 10% seats in the parliament. Now, this is why other countries, mostly countries which were formerly colonized by the UK, use a different system, namely the so-called single transferable vote. In that system, you still have districts, but the districts are quite larger, and they do not just elect one candidate, but multiple candidates. For instance, here in Australia, the Northern Territory elects 2, whereas Victoria down there elects 12 candidates. And in principle, this should lead to a much more proportional outcome. And at least here, it seems kind of proportional. There are multiple parties, including small parties, which get seats. Now, before we talk about STV and proportionality axioms, let's quickly define our model. And this is a more simplified version of what we have in the paper. In our model, we have some voters, n of them, some candidates, and the voters possess an ordinal ranking over the candidates, a complete ordinal ranking. So the voter says, this is my favorite candidate, then I like the next one, then this one, and so on. And we want to elect exactly k of the candidates. So in the Australia example, in Victoria, the k would be 12. So we want to elect 12 candidates. Now, STV, very, very simplified, works as follows. While we have less than k candidates selected, we check if there's somebody with more than n divided by k first place votes. So let's say if we have 100 seats, then 1% of the first place votes. If there is one, we take this candidate in the committee. We delete 1% of the voters who rank this candidate first. And otherwise, we simply delete the candidate with the least first place votes. Why is this proportional? Naturally, we are not the first ones asking this question. And there's an axiom for this. So let's say a way to describe why an outcome chosen by STV is proportional. And this is called proportionality for solid coalitions. And this tries to mimic this idea that an alpha percent of the voters should be able to control an alpha percent of the committee. So committee satisfies this proportionality for solid coalition if there is no solid coalition, that is, a group of voters who are large enough to deserve L seats. This is this L times n divided by k. And who have a common prefix, and prefix here means up to reshuffling of candidates, then this group of voters should have at least L, or if this prefix is not large enough, the entire prefix selected in the committee. So a group of voters who are, in some sense, forming a solid coalition, you can think of it as like having people from the same party ranked up top or something similar. They should get something they deserve. And STV satisfies this. Let's do a very tiny example. Here, we have 6 voters and 4 candidates, and we want to elect 4 candidates. So n divided by k is 1.5. So the first 3 might be able to, should deserve 2 candidates. So for them, out of A, B, and C, 2 should be selected. Whereas for the last 3, out of E and D, exactly E and D need to be selected. So the prefix does not need to be like in the same order, but it just needs to be some prefix up to reshuffling. So A, B, and C, we just A and B or B and C, any combination of them is good. Now, this proportionality axiom has a downside. Namely, and this was noticed, for instance, by Tiedemann in 2006, it is not very robust. So this requirement that they form a solid coalition or have the same prefix is not very robust to changes, right? If you just add like a single candidate in one of the voters, this would destroy the solid coalition, since they would suddenly no longer have the same prefix. As a very simple example, consider the following case. We have 4 voters and we want to elect 2. So 2 voters deserve 1 candidate. Here, we see that the first and the second voter, they both kind of like B and C, but they have a different first choice. So one has A as a first choice and the second one has E as a first choice. Same for the third and the fourth voters. So if you look quite carefully, you cannot find any prefix of any voters which is the same, except for all possible candidates. And or for the third and the fourth, the first 5 candidates. This is kind of bad, not what we want, right? So, for instance, in this example, we could select DNF. And DNF could also be selected by STB. For instance, it would first delete B and C, since they have the least first choice votes. Then that could delete A, then select D, then delete E, and select F. And this kind of does not feel proportional, right? Since the first and the second voter are quite ignored. They just get something at the very end of their list. They have something that they would both prefer, but still they don't get it, since they ranked something, just a single candidate, differently. Now, how do we formalize this? Well, we take a short detour to the much more recent model of approval preferences. And there's a great book on this topic, on proportionality and approval preferences and Multiwinner voting by Martin Lackner and Piotr Skowron. And it's freely available on the internet, so I would recommend to check it out, and it's a great resource. In this model, we again have n voters. We want to select k candidates. But now, instead of a ranking, the voters have approval sets. So they tell you, I like these, let's say, 3 candidates, and then another voter will tell you, I like these 4 candidates. We want to, again, select a committee of size k. Now, the PSC I showed you earlier is much older than the axioms for approval preferences, and the axioms for approval preferences were inspired by PSC. Here, we now replace this solid coalition requirement by something we call cohesiveness. We have a group of voters, we call it L cohesive, if they're again large enough to deserve L seats, and if they have L people in common. So again, think of it as them like approving L people from the same party. So the intersection of the approval sets is at least L, contains at least L candidates. Now, we say that a committee satisfies the EJR axiom if we cannot find an L cohesive group, all of which have less than L people approved, but they are L cohesive, so they would kind of deserve L people. So they have all less than L, but they would deserve more than L. And that's something we don't want. Whereas for PJR, this is a slight weakening. We just simply say there's no L cohesive group for which out of all of their approval sets, so it does not need to be from a single candidate, but like from all of them, less than L candidates are selected. So this group is, let's say, underrepresented. These are the 2 main axioms that, let's say, came out of a large line of research in proportionality with approval preferences. Now, they have similar downsides to proportionality for solid coalitions. They, just like proportionality for solid coalitions requires these prefixes, they require these L cohesive groups with the large intersections. And if you do experiments, this does not really heavily discriminate. Further, you kind of need to solve a sort of click problem to even find these L cohesive groups. So verifying whether a committee satisfies these axioms is not possible in polynomial time. So that's also kind of bad. So we try to do something which is verifiable in polynomial time and does not need this large degree of cohesiveness. And our main idea is to shift the focus from groups of voters to groups of candidates in the following sense, that we say that for any unchosen candidate, there should be no proportional reason to be included. So no unchosen candidate should be able to say, well, I would be much more proportional than these candidates chosen. How would we do this? In practice, we do this by pretty much just removing the cohesiveness requirement, so the requirement on the intersection. We say that the committee satisfies EJR+, and if you have a better name, send me an email, or maybe write it in the YouTube comments. Say that a committee satisfies EJR+. If there's no unchosen candidate, and group of voters approving this candidate, so NC is the set of people approving the candidate, such that they are large enough to deserve L people, and they have less than L. So we simply remove the requirement that they need to have L people in the intersection. We just want them to be able to say, well, we have all less than L, we are large enough to deserve L, and there's somebody we have in common. Why didn't you select them? This seems very unfair. And similarly, for PJR, we can define PJR+ similarly by removing cohesiveness and just saying we have a group of voters who all approve one candidate in common. They would deserve L, but out of their union of their approval sets, we just have less than L people selected. So we shift the burden from the voters to the candidates, and the candidates should witness proportionality or not proportionality. Now let's do a very small example here with 8 voters and 4 candidates. So n divided by k is 2. C1, C3, C5, and C7 satisfies EJR. Now we'll not calculate this through, but you cannot find any large cohesive groups here. But it doesn't satisfy EJR+. Namely, if you look at voters 2, 3, 5, 6, and 7, and 8, and candidate C4, then this group is large enough to deserve 3 candidates, but they all just have 2 candidates approved. So they would be able to say this is very unfair. We would be able to deserve 3, and there's a large candidate we all have in common, but this was not selected. So there's maybe something wrong with our election. Now, by definition, this implies EJR, and contrary to EJR+, which is co-NP complete to verify, this can be verified in O of n times m, or even in linear time in the instance size. And we can compute it by a very simple greedy rule. You can check it out in the committee, and it's always satisfiable. And all the rules which previously, or pretty much all the rules which previously satisfied EJR also satisfy EJR+. In fact, you can maybe show in some sense that any natural rule satisfying EJR or PJR also satisfy EJR+ or PJR+. There are a few examples, but these rules might not be considered natural. Now we go back to ranked preferences. We have this example again, where DNF might be very unfair, but can be selected by STV. Now, what our new idea is, we want to take this ordinal instance, and we want to convert it into approval instances. How do we do this? We simply go over every prefix. So first the prefix of length 1, then the prefix of length 2, length 3, so on, and treat them as an approval instance. So first, the first voter would approve A, the second would approve E, third D, and fourth F. Then would B for the first 2 and C for the second 2, and so on. And we would require that for each of these instances, we should satisfy our approval proportionality axiom. So we convert ranks into approvals. Now, we do this with PJR+ at first. So we say that it satisfies PJR+ if for each of these prefixes, the corresponding approval election in which you approve your top R candidates, the committee we chose satisfies PJR+. And this can also be satisfied, by the so-called expanding approvals rule by Aziz and Lee. And we show this via a more general statement about the so-called axiom of priceability. You can also check this out in the paper. Now, the natural first thing to ask is, why can't you do rank EJR+, so using the stronger axiom? And there's a very simple example where it fails, namely here, for simply 2 voters and 2 candidates to be elected. For the first prefix, we would require A and D to be selected. But then for the 3 prefix, 1 and 2 are too cohesive, so to say. So even for EJR, we would need to select either B or C. So we would need to select A, D, and B, but we only have 2 seats, so this is not possible. So rank EJR plus cannot be satisfied, and it's a nice open problem, so to say, to find an axiom which is stronger than rank PJR plus and still satisfied. Now we did some experimental results, and in these experiments we found that EJR plus is indeed much less likely to be satisfied by a random committee than the other 3 notions we talked about. So if you sample, let's say, from these random models which were defined in the literature, you sample a random committee, the probability of this committee satisfying EJR plus is much lower. And you can see it here in the dark green line. The dark green line is EJR plus, and this dark green line is, for a large part, much lower than the other axioms. Also, curiously, you can observe here that EJR and PJR plus are logically incompatible. So they do not imply one or the other. So you can see it on the left side that sometimes the red line is below the orange one, and vice versa. Now there's a lot of further content in our paper. Namely, we have a generalization to participatory budgeting, which is a cool new topic dealing with, let's say, a new democratic paradigm, which tries to divide a budget among projects based on votes of people. So you can think of it as multi-winner voting, in which the candidates have costs, and there's a budget which can be spent. So like a knapsack problem. Naturally, with knapsacks, everything is much more difficult, but if, at least for one special case, we were able to provide a similar generalization. We also generalized the proportionality degree, which is a, let's say, notion to assign a number to a committee to say, this is this much proportional. And the old notion of proportionality degree had similar weaknesses as the EJR and PJR axioms, namely it required cohesiveness, was very hard to compute. So we generalized it. What we did was just, as for the other axioms, we just removed cohesiveness. And now it's much easier to compute. Further, as I told you already earlier, we have a very simple rule which can compute EJR plus outcomes. And this rule is so simple that it doesn't really need any arithmetic or much else. And using this rule, we can define a fast algorithm for a querying setting defined at IIII earlier this year, which is faster than the best known algorithm so far, since we can save a lot on, let's say, computing stuff. Further, we generalized the notion of priceability to ordinal preferences and used it to show that this rank PJR plus axiom is satisfiable. There's a lot more hiding in the paper. For instance, we have weak preferences as well, which, let's say, generalizes approvals and ranks. And I would suggest you to check it out. It's on arXiv. So what we did is we defined a novel way to define proportionality axioms, not by going over groups, but by going over unchosen candidates and saying that no unchosen candidate should be able to witness, let's say, a proportionality violations. Our axioms are efficiently verifiable, sometimes even in linear time, and much more discriminating than previous axioms. In the paper, we have extensions to various topics such as ordinal preferences and participatory budgeting. And also quite important for some people, we found the first proportionality axiom, which formalizes perceived flaws in the widely used rule of STB. This doesn't mean, of course, that STB is a bad rule, just that there's maybe something one need to watch out with STB. Now there's a few open questions, namely people like to characterize stuff. And for the notion of PSC, there is a characterization, also by Aziz and Lee. But for anything stronger or anything in the prover world, there is none. Can we find a characterization, a nice one? I think that would be quite cute. Can we find a faithful EJR generalization, since rank EJR plus doesn't work? Is the notion of PSC compatible with candidate monotonicity? That's a very tricky open problem. Candidate monotonicity means that if you swap a candidate in the committee up, afterwards it should still stay in the committee. Seems very simple, and well, and of course that should be satisfied, but no known rule satisfying PSC, or of course rank PGI plus satisfies this, and they all break very easily, but no general impossibility has been found yet. And finally, can we find a verifiable generalization of EGI plus, which works for participatory budgeting, and not just for the one setting which we found, but for instance, for general utilities, so people assigning values, or for approval utilities, something like this. We were not able to do it, but I think that would be very important, since there's a lot of research going on in participatory budgeting and also a lot of experimental research. But for this experimental research, it's very hard to actually compute the proportionality notions, since instances can be very large with a lot of money. Okay, thank you for tuning into the talk. If you have any questions or want to talk to me about this problem, send me an email. You can find me on Google. I should be the first person there. And thank you very much for listening.